Hi, Diana.
Hello.
How are you tonight?
Very tired.
Are you? All right, I just got these, so I haven't really had a chance to look at them.
Yeah, sorry about
Is
that.
this page 1 or page 2 here?
Page 2. I already completed page 1.
Okay, so we want to start on these?
Yes.
All right, which one? I want to start on which number, 4 or?
I believe I can do 4 by myself.
Okay.
I believe I can also do 5.
Okay.
Some of these I'm not quite sure what.
5 looks relatively straightforward. Here, let me bring up my drawing tablet. We'll just briefly, we don't need to do the whole problem, but we can set some of these up just to make sure you can do them. All right, so 5 gives us an expression. First of all, gives us an integral that's not a function of x.
Right.
In other words, you can't do this unless you know what y is as a function of x.
Yeah, they said substitute
12
over x.
So that means we can write this as 12 pi over x, whoops, excuse me, 12 over x squared times pi. And we can even take the pi outside. You can always take constants outside of an integral. You cannot take variables outside.
Right.
Okay. So do you know how to take that integral?
Yes.
Okay. Just apply the power rule.
Yes, I believe I can do that.
Okay.
By myself, if need be.
Okay, so you can come up with the integral.
Mm-hmm.
Okay. What other problem you want to look at here?
And 6 and 7 depend on 5.
In problem 3, you gave an estimate of the exact volume.
Right.
Which means that instead of taking the integral, you must have used discs or washers or something to approximate the volume. Correct?
Yeah.
So 6 is wanting you to compare your approximated volume with the exact volume. 7, by what percentage was the original estimate off? Gives you the formula. Put your approximate minus the exact over the exact, gives you that error percentage.
Right.
How about 8?
I can do, since I can make the sketch and then I can integrate it.
Yeah, you don't really need to be able to make the sketch on 8. In other words, as long as you know that the square root function is going to do something like that.
Oh, yeah.
And if we're going to integrate that between 0 and pi, then it's just a question of integrating that formula.
And then finding the exact volume.
From 0 to pi. But, of course, we need to, or after we rotate it about the x-axis, what are we going to slice it up into? Discs or washers or what?
Discs.
Right. So it's not the integral of the function. Each disk has a volume of pi r squared. So, and r is that measurement right there, which is y. So
right.
it would be pi times that squared. So actually it's pi times 3 plus sine x. And now it's much easier to integrate even. Now, we would have had a hard time integrating that without a calculator.
Right.
But once you square it, because we're using disks, then it becomes quite integrable.
Right.
Using the trig functions. So that one's actually pretty easy too. In terms of the sketch, I suppose we would need to know exactly what that looks like. I've drawn just square root of x. So the square root of sine x, I don't know, I guess I'd have to graph that on a calculator maybe. If we think about that for a moment, the inside of this is going to vary from 2 to 4. So we're going to be taking the square root. The answer is always going to lie between square root of 2 and 2. There's no way y is outside of that range, because the lowest sine x can ever be is minus 1, the most it can ever be is plus 1. So we're going to go from the square root of 2 to the square root of 4 on the y-axis, and it's, I guess, must do something like this. Yeah. And then, of course, if that is rotated over the x-axis, then you end up with a figure that looks like that you could build with a bunch of disks. It's the one thing of calculus that I really think would be helpful is when you're doing these volumes of revolution, if you had a model. If I had the right tools, and if we were in person, I would take out a bunch of coins and I would put them together to look like this solid. Right. These would be the quarters, those would be the nickels, those would be quarters, these might be pennies. In other words, I could arrange a stack of coins to exactly look quite similar to what this solid of revolution is going to look like. And being able to picture that is really important with calculus and determining volumes. Right. Sometimes there's holes in these objects, in which case you have to use washers. Sometimes there's no holes, in which case you use discs. And there's other things that you can use also. All right, let's see. What's the formula for the volume of a sphere?
Isn't it volume equals 4/3 pi r cubed?
Yeah, and here I'll tell you something that's interesting. The surface area of a sphere is the first derivative of that.
Huh.
And I don't know if that's accidental or that's the way there's a reason for that. In other words, a surface area isn't always the first derivative of volume. So I think it's accidental with this, although I doubt that it's accidental because it's a sphere. That's such a fundamental shape and object that I kind of think there's a reason why the surface area is the first derivative of volume. So, determine the exact volume of a sphere with a radius 2. Well, that's not too tough. Approximate your volume to 4 decimal places.
Also not that much of a
at all.
problem.
I don't even know why those kind of problems would be on here, but...
No idea.
Okay, number 12. Okay, that represents the equation of a circle, center at the origin. Suppose we wanted the equation for the top half of that function. What would that equation be? Solve this for y. What do you get?
This one, I'm not quite sure how
No? That's the first thing.
this would happen.
Okay. And now you take square root of both sides.
Okay.
So there we've solved it for y. And why is that a circle? Well, the plus side of it is that. The minus side of it is that. So really the equation of a circle is actually a composite function. It's a combination of the top half of the circle, which is a function, the plus square root of that, and the bottom half of the circle, which is a function, the minus square root of that. So when they say, what is the equation for the top?
It's the positive.
Yeah, just the positive square root.
And we could substitute r for 2. Right?
Yeah, well, for number 12, it doesn't say what r is. It's just a variable. Oh, no, it does show it. It's 2. Yeah, I didn't see that. Yeah, so the real function is 4.
Yeah.
But the key is we're talking the top half of it, of the circle.
Not the bottom half.
Right. And that's why the equation of a circle is not a function. It's a relation. But if you look at the top half only, that is a function, as is the bottom half only.
Huh.
Okay. What else do you want to go over?
Okay, now it becomes more difficult.
Okay. You have some problems you can verbalize, or I only got these 2 pages.
Yeah, those are the only 2 pages that I haven't done.
Okay. What part becomes more difficult? Which? In other words, 8 through 12 were relatively easy.
Yes.
Want to go back and look at 4 or 5 or the other page?
Okay, 13 I could probably do.
I don't have a 30. Do I have a 13?
It's the second page.
Let's see. There's my page 1, only goes to 12. Oh, okay, I'm sorry. I thought both of them were the same. Oh, now I get it. So I did have more. All right, let's have a look at this. Hi, come here. Come here.
So I could probably do 13 on my own.
Okay. In other words, when we take the half circle and rotate it about the x-axis, what do we get? What kind of figure?
A circle?
Sphere. No. Yeah. No, you should get a sphere. Yeah.
Right.
A sphere of radius r. Everywhere on that thing it's going to have a radius of r.
Right.
Okay, so let's see
Though I may have trouble with 14.
Okay. Well, and let me see what they mean. Make a series of loopy ovals to represent the resultant solid of revolution if the graph were rotated about the x-axis. All right, I think what they mean by that is after you rotate it, it's going to look like that. And then to figure out the volume of that, these loopy ovals are the disks. And this is where being a good artist is helpful, and I'm not one, so I apologize. But anyway, we could make up a sphere with a bunch of coins, right?
Right.
Put the dime on this side, and then a penny, and then a nickel, and then a quarter, and then a nickel, a penny, a dime. Put them all together, we would have something that pretty much resembles a sphere. Wouldn't be smooth, but you get the idea. Right. That's how we're going to figure out the volume of the resulting object.
Right. So I could probably do that myself since I have what y equals.
Okay.
And
yeah, what you're going to discover when you do 13a is, well, probably C, is that when you use calculus, when you start with 12, the equation we had for y, and you use calculus to calculate the volume of that object that you get, you're going to end up with 4/3 pi r cubed, which we know is the volume of a sphere. So we better get that.
Right.
Okay. So let's set up C. So we know we're going to integrate. We're going to go from minus r to r, whether it's 2 or not. We're going to go from minus r to r. We're going to integrate. I guess we better go from minus 2 to 2, because since I'm going to fill in a number here.
Right.
I don't know that I need to fill in that number. I could probably leave it at r.
I mean, D asks why I chose my boundaries like the way I did, but...
Okay. Well, let me back up here and let's just do a standard r here. And then that puts r squared in there. And that is y. Well, each of our disks is pi r squared, so we're going to have to square that. So we really have from minus r to r, the pi we can take out there. After we square that, we have r squared minus x squared dx.
Right.
Integrate that. Evaluate it from r to r, and you're going to end up with 4/3 pi r cubed.
Right.
And notice when we integrate this part here, we're going to add 1, so it becomes x cubed over 3. So that's where the 3 of the 4/3 comes in. The pi, you're going to end up with 4/3 pi r squared by the time you substitute these r's in for the variable when you get done.
Right.
All right, let's see. Set up the appropriate integral. Okay, we did. And I suppose maybe since we know it's 2, we'll go from 2 to 2, and we'll make that 2. Now it's pretty easy to integrate that.
Right.
And you said, explain what value of x you chose as your boundaries and why. Well, it's clear x goes from -2 to 2 from this picture, right? In other words, you're always integrating on the axis of the skinny side of the object that you're using. We're using disks that are perpendicular to the x-axis. That means the skinny part of the disk is perpendicular to the x-axis. That means we're always going to integrate that with regards to the x-axis. There are integration problems where you integrate with regards to the y-axis, not the x-axis. Have you seen any of those?
No.
Have you come across that yet? Okay.
No.
An example would be, let me see if I can remember what a good example is. If I want to figure out the area between those curves, it's better to lay out horizontal rectangles rather than vertical rectangles. With horizontal rectangles, I'm integrating on the y-axis. So this curve would be a function of y. This curve would be a function of y. And I would take the integral of g of y minus f of y, the other curve, dy. And I would go from 2 to 5. In other words, you don't have to integrate on the x-axis. You can integrate on the y-axis also. Whether you're finding the area between curves or whether you're finding the area of a solid object. In other words, if I had an object that I was rotating about the y-axis, okay? Let's take that function, rotate it about the y-axis, making that bullet-shaped thing. Well, now my disks really need to be this way. So I would want to integrate that along the y-axis, going from 0 to whatever that point is there. Let's say that's 3. And you would have to take this function and define it as a function of y. You cannot integrate a function of x with a dy. In other words, this doesn't make any sense.
Right.
You have to have this variable be the same as that variable. So if you're integrating along the y-axis, you're integrating a function of y, not a function of x. Just thought I would mention that. Has a little bit to do with how you choose those boundaries. Evaluate the integral, express your answer exactly. So we're evaluating that integral, right? Well, we know what the answer is, right? We know the answer is 4/3 pi r cubed, so it's 4/3 pi times 8. So the answer is 32 pi over 3. Shall we see if we get that?
No, I can get it.
Okay, you know how to do that integration and evaluation.
Yes.
But it's helpful to know what the volume should be based on what we know the volume of a sphere to be. So we're looking for 32 pi over 3, okay?
Although I may have...
And f How does E compare to the answer in 10? Should be exactly the same.
Right.
Okay. Comment on what this tells you. That's swell. That's what my comment is. I hate questions like that.
Yes.
I mean, if they're equal, what's your comment supposed to be? I can't even imagine what your comment would be other than they're equal. All right, let's look at 14. Okay?
Okay.
So what they're saying is that f triple prime is equal to the integral of f fourth prime of f. Almost. Well, no, actually. And we know that, hold on. If we take the integral of the fourth derivative, what we get is the third derivative plus c, right?
Right.
Okay. And they're telling us that the fourth derivative evaluated, or rather the,
Oh, so, okay,
you should be able to determine f triple prime of x. Well, let's see. This is supposed to be the third derivative. When you take the antiderivative of that, you get that. So we know that the third derivative evaluated at 0 equals 3. So I think that tells us, hold on a moment. The fourth derivative equals minus 1. So yeah, what they're going to do here is step by step get you back to the original function.
right. Slowly but surely.
Yeah. Let me think about this for a second. This is actually a fairly common problem, but they usually give you the function. Better example of this is actually velocity and acceleration and position.
Right.
If you know the acceleration of an object, then you can integrate that, and if you know a starting velocity, you can come up with the velocity function, and if you know a starting position, then you can come up with the position function. So here we don't know the function, but we know that its fourth derivative is minus 1. So what is its third derivative? In other words, we know that we have to integrate the fourth derivative to get the third derivative. Okay, so if the fourth derivative is equal to minus 1, yeah, go ahead.
Hold on, I have to go to the door really quick since my sister's there.
Okay, go ahead.
Okay, I'll be back. Uh, 7586.
Okay. I can tell you how to do these real quick. I know that we're out of time here, but I think I can tell you how to finish these up.
Right.
The third derivative is the integral of the fourth derivative, right?
Right.
They're telling us that the fourth derivative of x is minus 1. So if I integrate minus 1, I get minus 1x plus c. That's my third derivative.
Right.
Well, they're telling me that the third derivative evaluated at 0 is 3. Well, if I plug in 0, the only way that can be is if c is 3.
Right.
So my third derivative is minus x plus 3. There's my third derivative right there. Work backwards using the same logic. The second derivative is going to be the integral of minus x plus 3, which is minus x squared over 2 plus 3x plus c. They're also telling us that this thing evaluated at 0 is minus 2. So when I plug in 0 for x, I get minus 2, which tells me here c is minus 2. So now my second derivative as a function of x must be minus x squared over 2 plus 3x minus 2. You'll notice that if we plug in 0 for x, we get minus 2. Go back, figure out the first derivative using this logic, and then the first function using this logic. And each step produces a c, which you can calculate using these conditions up here. You with me?
Yes.
Okay. You good to go on that problem? Because I think that whole problem is probably just doing that all the way down. Yeah. In other words,
Right.
getting to D, you end up finding what f of x is.
Right.
All right. I will let you go, I guess. You good?
Yeah, I think I'll be good.
Okay. Talk to you next Thursday.
All right, bye. Thank you.